Fundamental structure of the universe. Quantized nature of spacetime. The physical universe operates through a quantized mechanism characterized by discrete blinks occurring at an approximate frequency of 1.1 terahertz. This granular nature of spacetime indicates that traditional views of a smooth, continuous spacetime are fundamentally flawed, necessitating a quantum model where spacetime consists of discrete units. The implications are profound, suggesting that phenomena such as motion, energy transfer, and field interactions must be reconsidered within this granular framework. The granularity of spacetime suggests that each blink represents a minimal unit of time and a fundamental unit of space, fundamentally altering our understanding of distance, velocity, and acceleration. This model suggests that at the most fundamental level, these classical concepts need to be redefined in terms of quantized spacetime interactions. Reconceptualizing time and gravity. Time is an emergent property, postulate 5. As perceived by human consciousness, time emerges from the interactions within the quantized spacetime framework. This emergent nature of time suggests that what we perceive as the past, present, and future are effects of our cognitive interpretation of quantum events fundamentally outside such temporal distinctions. The implications for technology, especially those approaching the singularity, include potential time dilation effects, where processes can appear to halt or significantly slow down due to extreme information processing rates and technological advancement. Quantum gravity derived from space-time blinks. Gravity's strength varies with the quantum blinks of the universe, alternating between its maximum strength and zero. This model of gravity provides a novel explanation for quantum gravity that does not require its unification with other fundamental forces in the traditional sense. A fluctuating gravitational model suggests new approaches to integrating gravity with quantum mechanics, potentially offering solutions to long-standing problems in physics by proposing that gravitational effects are tied directly to the quantum state of the universe. Cosmological consequences and unified particle theory. The illusion of an expanding universe. The perceived expansion of the universe is a misinterpretation of the cyclic redefinitions of space at each quantum blink. This redefinition creates the illusion of expansion, similar to how dynamic updates in software can introduce new features without changing the system's physical size. Observational phenomena such as redshifts, traditionally interpreted as evidence for expansion, are instead manifestations of dynamic changes in the speed of light and other constants influenced by the state of the quantized universe. Framework for 1024 elementary particles. The array of particles proposed in the 1024 QM model are manifestations of the energy states possible within each blink of the universe. These states are transient, highly dependent on the conditions at each quantum event, and require rethinking particle stability and interaction. The detection of these transient particles and validation of the 1024 QM model would require advancements in particle detection technologies, particularly those capable of synchronizing with or operating at the high frequencies of quantum blinks. Implications for quantum mechanics and field theory. Revision of quantum mechanics. Given the quantized nature of spacetime, quantum mechanics must be reformulated to account for the fundamental discreteness of the universe. This includes reevaluating concepts like superposition, entanglement, and wave-particle duality, which may behave differently under a quantized time framework. Quantum fields, traditionally conceptualized as continuous throughout spacetime, must instead be viewed as manifesting in discrete chunks during each quantum blink. This view alters the fundamental understanding of field interactions, particle decay processes, and the generation of virtual particles. New models of particle interaction. Particle interactions must be reinterpreted in a blinking universe, including fundamental forces like electromagnetism and the strong and weak nuclear forces. Each interaction occurs within discrete time frames, potentially leading to variations in force strength and interaction outcomes that are not accounted for in continuous models. This reinterpretation necessitates new mathematical models and simulation techniques that can accurately represent these interactions' transient quantized nature. These techniques can provide insights into phenomena that defy current physics models, such as anomalies in particle collision data. Experimental and observational strategies. Advanced detection and measurement techniques. New detection systems capable of operating at or above the terahertz frequency range are necessary to validate the quantist nature of spacetime and the variability of constants. These systems must be sensitive enough to detect minute changes in the physical constants and capture transient phenomena within each blink. Developing ultra-fast imaging and sensor technologies will be crucial. These technologies will need to capture data at rates sufficient to observe the universe's blinking, potentially leading to breakthroughs in understanding high-energy cosmic events and quantum gravitational effects. Cosmological observations. Astronomical observations must be re-evaluated under the assumption that cosmic phenomena are influenced by the dynamic constants and the quantized structure of spacetime. This includes reinterpreting the light from distant celestial bodies, cosmic microwave background radiation, and gravitational wave detection. Observational strategies should focus on detecting patterns or anomalies in cosmic phenomena that align with predictions from the blinking universe model, such as variable redshift distributions or unexplained periodicities in electromagnetic signals. Broader theoretical implications and future research. Integration with theoretical physics. Theoretical physics frameworks, including string theory and loop quantum gravity, must integrate the quantized dynamics framework to resolve inconsistencies with empirical data and provide a unified theory of everything. This integration promises a deeper understanding of the universe and potential applications in emerging technologies such as quantum computing, where the granular nature of spacetime could be exploited for more efficient information processing and storage. Philosophical and technological implications. The quantized universe model radically alters our philosophical understanding of reality, challenging notions of causality, determinism, and the nature of existence itself. Technologically, understanding and manipulating the quantum blinks could lead to advancements in energy generation and telecommunications, and even potentially allow for technologies that can manipulate the fundamental structure of reality. Interdisciplinary impact and cross-domain applications. Impact on computational physics. The quantized dynamics of spacetime necessitate advancements in computational physics, specifically in developing algorithms that can simulate quantum granular phenomena over cosmological scales. These simulations will be crucial in predicting and visualizing the effects of quantized spacetime on classical and quantum systems. Enhanced computational models must incorporate the variability of fundamental constants, requiring dynamic adjustment of these values in real-time simulations. This could vastly improve the accuracy of predictions in high-energy physics, astrophysics, and other areas dependent on precise physical constants. Quantum computing and information theory. Quantum computing stands to benefit significantly from a deeper understanding of the quantized universe. The principles of quantum mechanics integrated with the blinking spacetime model could lead to new forms of quantum bits that are inherently stable, owing to synchronization with the universal blink rate. In information theory, information storage and retrieval must be rethought to potentially exploit the discrete nature of time and space, leading to more efficient data processing methods that align with the fundamental temporal granularity of the universe. In experimental physics, cutting-edge advancements are crucial for exploring the frontiers of our understanding. High-frequency experimental setups are now required to directly observe the effects of the quantized spacetime blinks operating at or near the terahertz frequency. These setups will likely involve innovative particle accelerators, laser systems, and electromagnetic field detectors designed to operate at these extreme frequencies. Such experimental systems must possess high temporal resolution and sensitivity to detect slight variations in physical constants as spacetime blinks, providing empirical support for the Unified Quantized Dynamics Framework, or UQDF. Observations of high-energy cosmic rays and other astrophysical phenomena can indirectly show a quantized universe. Anomalies in the energy spectra and arrival times of these rays might reveal interactions with the discrete structure of spacetime. Advanced monitoring of cosmic events should therefore focus on detecting patterns that align with predictions from the quantized dynamics model, such as specific energy thresholds where unusual phenomena occur due to the granular nature of spacetime. The implications for the theoretical foundations in physics are profound and far-reaching. General relativity and quantum field theory frameworks must be reconsidered in light of a quantized and dynamically changing spacetime. This may involve formulating a new theory of gravitation that incorporates both the principles of quantum mechanics and the discrete nature of spacetime. These theoretical revisions will likely converge towards a unified field theory that seamlessly integrates the forces of nature within a quantized temporal spatial framework, resolving current inconsistencies between large-scale cosmological phenomena and small-scale quantum phenomena. Accepting a quantized, blinking universe model necessitates a philosophical shift in our understanding of reality. It challenges the classical deterministic view and embraces a probabilistic, discrete framework in which reality is fundamentally non-continuous. This shift would impact various philosophical disciplines, prompting debates concerning the nature of existence, the flow of time, and the underpinnings of causality and determinism in a universe where the fundamental structure is quantized. Looking towards future directions in interdisciplinary research, the integration of the unified quantized dynamics framework with emerging technologies is crucial. The discrete nature of spacetime could be harnessed to develop materials with novel properties, such as metamaterials that can manipulate electromagnetic waves in unprecedented ways. Technologies that exploit the discrete nature of spacetime, quantum teleportation, or gravity manipulation devices could theoretically become possible and revolutionize fields like transportation, telecommunications, and energy. The fundamental changes proposed in the UQDF necessitate revamping educational curricula in physics and related sciences. This education should not only inform on the latest scientific models, but also encourage critical thinking about the implications of a quantized universe. Public outreach and communication become essential. These concepts challenge traditional understandings of the universe. Effective communication strategies will be crucial in explaining the significance and implications of these findings to a broader audience. Ethical and societal considerations. Ethical implications of new technologies. The potential technologies enabled by understanding and manipulating the quantized dynamics of spacetime raise significant ethical questions. These include concerns about privacy, security, and the potential for misuse of technologies like time manipulation or advanced surveillance systems that could emerge from this new understanding. Establishing robust ethical guidelines and regulatory frameworks will be essential to ensure that these technologies are developed and implemented in ways that benefit society while minimizing risks. Societal impact and policy development. As the implications of the UQDF permeate through society, influencing technology, philosophy, and daily life, it will become crucial for policymakers to understand and anticipate the changes that might arise. This understanding will be necessary to craft policies that help society adapt to these advancements effectively and ethically. Policymakers must collaborate closely with scientists and technologists to create informed regulations that guide the development and use of technologies derived from quantum spacetime dynamics, ensuring they align with societal values and global standards. Long-term scientific goals and global collaboration. Establishing international research collaboratives. The global nature of the scientific challenges posed by the UQDF suggests a need for international research collaboratives that pool resources, expertise, and data to explore these phenomena more effectively. These collaboratives would accelerate the pace of discovery and foster a spirit of cooperation that transcends national boundaries, focusing on shared human interests in understanding the universe. Development of a global quantum research infrastructure building, a global infrastructure for quantum research, comprising advanced laboratories, telescopes, particle accelerators, and computational facilities, will be essential to test the predictions of the UQDF and explore its practical applications. This infrastructure will serve as the backbone for the next generation of scientific advancements, providing the necessary tools to explore the quantum granular nature of spacetime and its applications across various fields. Bridging quantum and classical realms. Harmonizing quantum mechanics and classical mechanics. The discrete nature of spacetime posited by the UQDF necessitates bridging quantum mechanics and classical mechanics. This integration must occur by developing hybrid models that accurately represent phenomena across all scales, microscopic to macroscopic, considering the quantized structure of spacetime. New theories will need to emerge that can reconcile the apparent contradictions between classical physics's deterministic world and quantum physics's probabilistic nature, using the foundational concept of a quantized universe as a unifying thread. Implications for chaos theory and complex systems. The understanding of chaos and complex systems is profoundly affected by the UQDF, as these systems may exhibit new behaviors under a quantized time framework. This could lead to revised theories in nonlinear dynamics and better predictive models for complex systems, such as weather patterns and economic markets. Research in these areas should focus on how the discrete changes in spacetime influence emergent phenomena and the stability of complex systems, potentially leading to new approaches in managing, predicting, and optimizing these systems. Enhancing predictive models and simulation technologies. Advancing simulation technologies. Simulation technologies must be significantly enhanced to model the implications of quantized spacetime accurately. This involves developing new computational algorithms that can handle the high-frequency dynamics of the UQDF, allowing for both granular and expansive simulations. These advancements will enable better predictions and simulations in fields such as quantum computing, cosmology, particle physics, and even in everyday applications such as GPS and telecommunications that may rely on understanding the quantum properties of spacetime. Predictive models in quantum meteorology and geophysics. The field of quantum meteorology could emerge, applying quantum principles to atmospheric and geophysical processes influenced by the UQDF. This field would use quantum simulations to predict weather patterns, climate changes, and geological phenomena with greater accuracy. Research should explore how the quantum granularity of spacetime affects geological and atmospheric systems on a planetary scale, potentially revolutionizing our approach to predicting and managing natural disasters and global climate change. Quantum architectures and infrastructure. Development of quantum-enabled architectures. Future technological infrastructure must be designed to be quantum-enabled, incorporating materials and architectures that harness the unique properties of quantized spacetime for enhanced performance and new functionalities. Designing buildings, vehicles, and other structures that can interact with or are adaptive to the quantum properties of their environment, possibly using these properties to enhance stability, energy efficiency, or other desired characteristics. Quantum urban planning and development. Urban planning and development could incorporate principles from the UQDF to create living environments that are in harmony with the quantum nature of the universe. This might involve using new materials, energy systems, and design principles that optimize human health, energy use, and environmental impact. In this area could lead to the development of quantum cities, where all aspects of the urban environment are designed with an understanding of quantum principles. This would lead to revolutionary changes in how urban spaces are constructed, maintained, and experienced. Quantum biophysics and medicine. Quantum mechanisms in biological systems. The quantized dynamics framework suggests that quantum mechanisms play a crucial role in biological systems. Research into quantum biophysics could reveal how quantum blinks influence cellular processes, neural activity, and genetic mutations, potentially leading to a deeper understanding of life. Developments in quantum biology could lead to breakthroughs in medicine, such as quantum diagnostic techniques and treatments that target the quantum mechanical basis of disease processes, revolutionizing healthcare and treatment modalities. Enhancing drug development. With the insights gained from the unified quantized dynamics framework, pharmaceutical development could harness quantum simulations to predict molecular interactions at unprecedented levels of accuracy. This would accelerate the discovery of new drugs and improve their efficacy and safety profiles. Postulate 64. Quantum-enhanced computational models could predict side effects and interactions of pharmaceutical compounds more accurately, significantly reducing the cost and time associated with drug trials and regulatory approvals. Quantum economics and decision theory. Quantum decision-making models. The principles of quantized spacetime could be applied to develop quantum decision-making models that provide new frameworks for understanding economic behavior and market dynamics. These models would incorporate elements of quantum probability and uncertainty to predict economic phenomena better. Integration of quantum computing and economic modeling could develop highly sophisticated financial analysis and forecasting tools, offering significant advantages over traditional methods. Implications for economic policy: quantum economic models could influence policymaking by providing more accurate predictions of the financial impact of policy decisions. This would be particularly valuable in complex dynamic economic environments where traditional models fail to capture potential outcomes. Policymakers could use quantum economic simulations to test and refine policies before implementation, reducing unintended consequences and ensuring that policies are robust against various economic scenarios. Quantum environmental science. Quantum climatology. Exploring the quantum mechanical underpinnings of climatic systems could lead to a new field of quantum climatology, where quantum principles are used to model and predict climate changes with greater precision. This approach could enhance our understanding of complex climate interactions and feedback loops, potentially leading to more effective strategies for managing climate change and its impacts on global ecosystems. Quantum geoengineering. Applying quantum technologies in geoengineering could introduce methods for altering environmental processes at the quantum level, offering potentially revolutionary solutions to global warming and ecological degradation. Such technologies must be cautiously developed, incorporating rigorous ethical and environmental considerations to ensure they do not inadvertently cause more harm than good. Philosophical and theoretical implications. Redefining reality. The unified quantized dynamics framework challenges our traditional notions of reality, suggesting that the universe is a more fluid and dynamic construct than previously understood. This has profound implications for philosophical debates around the nature of reality, existence, and consciousness. Philosophical inquiry into the implications of a quantized universe could lead to new understandings of consciousness, the nature of time, and the interconnections between observer and observed. Theoretical implications for multiverse theories. The discrete nature of spacetime, as suggested by the UQDF, lends support to multiverse theories, providing a potential mechanism for the existence of parallel universes that interact or exist concurrently within a higher dimensional space. Future theoretical research could explore the connections between quantized spacetime and the structure of these potential multiverses, potentially revolutionizing our understanding of the universe and its many possible iterations.